been talking about is a normal distribution, but we've been applying it to a whole population. You know, if I knew the percentage of all refrigerators that only lasted 5 years, we had a certain proportion. What we are going to do in Chapter 8 is start extending that to smaller groups, because we know, in general, do we usually have the entire population to look at? No, we usually have a sample instead. So we have to take what we know about the normal distribution and apply it to a sample now. So just a question for you. If I wanted to find the average household income in the United States, and I take a survey of 10,000 households, will the mean of that sample be the same as the mean of the entire population? Probably not. Okay, there's a chance, but we know that if I just take a random group, it's probably not exact with the entire group. If I pick a different 10,000 households, will that be the same as the first mean I found? No. Every sample I get will likely have a different mean. So we have to figure out, how am I going to extend this to everything if every sample is going to have a different mean? So what we'll do is we'll look at a sampling distribution. It's just a probability distribution for all the possible values of a sample size. So when I talk about this, it seems a little arbitrary. We are actually going to walk through an example. This isn't an example like I would have you do on homework, but it's just showing us, what am I talking about when I talk about a sampling distribution of the sample means? What does that even mean? So we're going to take a scenario. And let's say I have 6 pumpkins displayed in a carnival guess the weight game booth. You are asked to guess the average weight of the 6 pumpkins by taking a random sample without replacement from the population. Okay, so my population is 6 pumpkins. We're going to try to guess the average weight of those 6 pumpkins by taking any 2 pumpkins out of that group and getting their average weight. Okay? So if I call my pumpkins A, B, C, D, E, F, here are the true weights of those 6 pumpkins. Can we find the actual weight of this whole population, or the actual average of this whole population? Yeah, let's do that. So the true mean, just so we have that for reference, if we add these all up, divided by the 6 pumpkins. So the average weight is 14 pounds. So let's see what would happen if I took a sampling distribution here. So I have to take every possible combination of 2 pumpkins. So I've started a table for you. We're going to fill in the gaps. So I could take pumpkin A and B. Okay, the weight of pumpkin A is 19 pounds, the weight of pumpkin B is 14. So to get to our average, we add them up and we divide by 2. Okay, so I'm going to save this probability for a second. I could do A and C. I did the same thing, took their weights, found the average. A and D, A and E. So we need to fill in some gaps here. The weight of pumpkin A is 19 pounds. The weight of pumpkin E is 10. So the average, 19 plus 10 divided by 2, 14.5. All right, I could take pumpkin A and F. So pumpkin A is 19, pumpkin F is 17. 19 plus 17 divided by 2? 18. Does everybody understand what I'm doing here? Every possible set of 2. So I could do B and C, B and D, B and E. So pumpkin B is 14 pounds, pumpkin E is 10. Add those together, divide by 2, and we get 12. B and F, so that would be 14 and 17. Add those up, divide by 2. 15.5. Okay, I could do C and D, C and E, C and F. So pumpkin C is 15 pounds, pumpkin F is 17. So if I add those up and divide by 2, 16. D and E. I left a couple blank. What are the other 2 combinations we haven't done?
D and F and E.
All right, so pumpkin D is 9, Pumpkin F is 17. Add those, we get an average of 13. Pumpkin E is 10, pumpkin F is 17. Add those up, divide by 2, and we get 13.5. How many different combinations of 2 pumpkins did I come up with? Count all of these. $15. So the probability of each of these scenarios would just be 1 in 15. Agreed? I'm just going to draw an arrow. I'm not going to actually write that every time. Okay, so in the next table, I took all of these average weights that we found. Did we have any repeat values? Like I had 14.5 showed up twice. Did anything else get repeated? 12 showed up twice. And otherwise, all my averages were different. Okay, so if I took, these are the different numbers I got for my average. So the probability of each of those, let's start with the 2 that got repeated. 12 showed up 2 out of the 15 times. The other one that got repeated was 14.5 showed up 2 out of the 15 times, and everything else just showed up once. So every probability is between 0 and 1. If we add all these probabilities together, it equals 1. So this is what we're talking about when we say a sampling distribution of the sample means. This is a probability distribution of every possible mean from every possible sample of that size. We're not usually going to create these samples. This is just to kind of illustrate what I'm talking about, where these numbers come from. All right, so here's a question. What is the probability that the sample mean is the population mean? What did we find for our population mean when we actually worked it out? At the very beginning, the actual average weight was 14 pounds. So what's the probability that we get 14 pounds from our sample? 1 in 15. So there is only a 1 in 15 chance that you will take a group of 2 pumpkins and get the right average mean. Okay, what is the mean of this sample? So if I'm talking about the mean of this sample, I'm asking you to add up all of my averages and divide by 15. Let's do that. Add them up. So it adds up to 10, divide by 15, and we get a mean of 14. Is 14 familiar? That was our actual mean. So this was the same as the actual mean. Okay, that could have been just luck. So let's try this again, but I'm going to take a bigger sample. So I'm going to say I have a sample of 5 pumpkins. I'm going to take 5 of those 6 pumpkins, find the average weight. So every possible combination of 5, A, B, C, D, E. So basically you're leaving 1 pumpkin out at a time. So I could leave out pumpkin F, I could leave out E, could leave out D, could leave out C. So the other combinations, I need to leave out pumpkin B. And I need to leave out pumpkin A. So if I find our averages, we have to take the weights of the pumpkins that we selected. Add them up and divide by 5. So how many different combinations, how many different groups could we form? 6. So the probability of each of these things is 1 in 6. Did I repeat any of my means this time? No. Everyone was different. They all had an equal probability of 1/6. Okay, so let's ask a question. What is the mean of the sample means? So if I want the mean of this, you have to add up all of those and divide by 6. And we get 14 again. So it kind of leads us to believe that when we take these sampling distributions, the mean of that is the same as the mean of the original population. How does the error in this compare to the error of the first? So in the first one, what was the probability that we got it right when we just took a sample of 2 pumpkins? The probability that the mean was the same as the population was 1 in 15. So in the first, there's 1 in 15 chance. In my second one, what's the chance that my sample mean is the same as my population mean? Right. The population mean is 14. If I look, the probability of getting 14 is 1 in 6. So what happened to the odds that you get it right? Did it go up or down? Up. I added more pumpkins into my sample and I had a higher probability of getting the actual mean. So basically what this, how do I want to say this? The sample size tells us the larger sample will lead to a smaller standard deviation, smaller spread. And we have already kind of talked about that before, earlier on. We said, we already know that the bigger our sample is, the closer it's going to look to the true population. Okay, and that's still true when we're talking about these sampling distributions. Basically, the larger it is, the better our data is going to be. All right, so this was just kind of some background to help understand what I'm talking about when I say sampling distributions of the sample mean. What's really important, what we are going to use, we're going to call these distributions for X bar the sample mean. So the mean for X bar we found is the same as the mean of the original population. The standard deviation for X bar, I didn't show you how to calculate this, but it will turn out to be the original standard deviation divided by the square root of n being our sample size. So just like everything else, we're not memorizing these. It's on our formula sheet. Chapter 8, first bullet, mean and standard deviation for the sampling distribution of X bar. And it's right there. If the original population, so I'm just going to say if the X's are normally distributed, so is X bar. So if I tell you the population is normal, we can assume, even if I'm talking about X bar, it's still normal, so we can do all of the stuff that we were just doing. take our x's, turn them into z's, and read the probability from the table. So let's try a couple examples. The weights of pennies minted after 1982 are approximately normal. So I told you it was normal. That means we can do all of our stuff. Normally distributed with a mean of 2.46 grams. So the normal original population mean is 2.46 and the standard deviation is 0.02. That's the mean and standard deviation of all pennies. So if I want the mean and standard deviation of the sampling distribution of 200 simple random samples. Okay, so I am talking about a sampling distribution. So that tells me I'm talking about that X bar. So if we look at our formula sheet, the mean of X bar is same as the original mean, so just 2.46. Standard deviation for X bar is the original standard deviation divided by the square root of n. What is n here? Try to keep 4 decimal places or more on this, because we'll use it to find our z-scores in a minute, and if you round it too much, it will throw off your other calculations. So just make sure you're keeping a few decimal places on sigma. So for the second question, what's going to change? Yeah, all I'm changing is the number of pennies, so it's only going to affect my standard deviation. My mean is still 2.46. The standard deviation is now 0.02, the original standard deviation, divided by the square root of 100. So we get 0.002. So now let's take this stuff and apply it to what we were doing yesterday with the normal distribution. So another penny example, I still have in my original population, we know it's normal, so it's the same setup as this example. The mean is the 2.46, standard deviation is the 0.02. So I want the probability that in a simple random sample of 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams. Okay, the first thing we have to do, I am talking about the sample mean. Anytime I see sample mean, I'm thinking X bar. So I gave you a mean and standard deviation, but that's not the one we need. We need the mean and standard deviation for the population we're looking at, which is X bar. So that has to be our first. We need the mean and standard deviation for the X bars. So mean is 2.46. Standard deviation is 0.02 divided by what? Square root of 10. We get 0.0063. I'm asking you to find the probability, the sample mean, so that's X bar, at least, what does that mean? Greater than or equal to 2.465. All right, this is the type of question that you would have had yesterday. I'm talking about X bar, so I have to use the mean and standard deviation that go with it. So I have to use the X bars. When I gave you an X, you had to turn it into a Z. So we have to find our Z first. So Z is our value minus the mean divided by the standard deviation. And And we're using everything from the X bar. Remember, Z values, we're looking on our table, so we can only do 2 decimal places. So we have to find the probability that Z is greater than or equal to 0.79. So the table gives us less than. How do we find greater than? 1 minus. Then we go to our normal distribution, so that table, and we're looking at 0.79. And so we should get 0.2148. Right, so the only difference on these problems, when I talk about the sample means, you have to find your mean and standard deviation for the sample means, and then it's exactly as before. Change it into a Z, read your probability from the table. Okay, so that is the only switch. Let's try a couple more of these. The engines made by Ford for speedboats have an average power of 220 horsepower and standard deviation of 15. A potential buyer intends to take a sample of 4 engines and will not place an order if the sample mean, so when I see sample mean, what am I thinking about? Sample mean, that's talking about the X bars, is less than 215 horsepower. What is the probability that the buyer will not place the order? So, I'm talking about sample mean, so I need the mean and standard deviation for the sample mean. The mean of the sample mean is the same as the original mean. What was my original? Yeah, it said the average was 220, so the average is your mean. Standard deviation. Original standard deviation is 15. Divided by the square root of n. How many am I looking at? 4. We're taking a sample of 4 engines. So that is my mean and standard deviation for X bars. Everybody know how I got those? So now I want to know the probability the buyer will not place the order. Okay, they will not place it if the sample mean, so if X bar is less than 215. So I just need to find the probability X bar is less than 215. So what do we do first? Have to get a Z. So that's our X minus the mean divided by standard deviation. Again, since this is X bar, you have to do the mean and standard deviation for X bar. If we round to 2 decimal places, that gives us negative 0.67. So I need the probability that Z is less than negative 0.67. Less than is what my table gives me. So we just look up the negative 0.67 and we get 2514. Is this okay? Do you guys want to try to set it up by yourselves or you want to do it together? Okay, give it a try. Take a few minutes, see if you can figure it out. So I told you it was normally distributed. I'm talking about a sample mean, so we have to have the mean and standard deviation for the sample mean. So that's the same as the original mean, which is 100. Standard deviation would be 15 divided by the square root of, how big is our sample? 10. And what does that give us? Keep more decimal places. Okay. So I want the probability that the sample mean is greater than 110. So first get the z. So 110 minus 100 divided by 4.7434. So we get 2.11. So I want the probability z is bigger than 2.11. So greater than, what do we have to do? 1 minus. You look up your 2.11, that's 0.9826. And so you get 0.0174. Is that okay? All right, so let's talk about if I made a probability distribution for rolling a dice. So how many outcomes are there? 6. What's the probability of each one? 1/6. Is that normal? Would that be a normal distribution? If you think about if you made a graph, so we can get we said the probability of each one is 1/6. How do I know from a graph if it's normal? What shape does it have to have? Well, this one has a rectangle, but a normal distribution is the bell shape, right? Symmetric. This is uniform because everything is the same. It's a rectangle. So if I were talking about rolling a dice, I couldn't just use my normal distribution because this isn't normal data. But as it turns out, I'm just going to tell you this rather than taking the time to actually create it and show you. If I made a distribution where I rolled my dice over and over again, so if I did samples of size 4, okay, so I'm going to roll it 4 times, then I'm going to find my average. Roll it 4 times, find my average. And I do this 200 times. If I find 200 averages, this is what the shape of that looks like. What does that remind you of? Yeah, that's kind of bell-shaped. Okay, if I change my n and I make it bigger, so I roll it 10 times, find my average. Roll it 10 times, find my average. And do that 200 times. It's a little more bell-shaped. If I roll it 30 times at once and find my average, it's even more bell-shaped. So the original distribution wasn't normal, but when I looked at my sample means, it was. So this is what's called the central limit theorem. So basically, as n gets larger, the data becomes more normally shaped. And we saw by the time we got to 30, it was pretty well perfectly normal, very close to it. So we are going to go with this assumption that no matter what the original data looks like. So if the original is normal, we don't have to worry about it. It's fine anyway. If the original data is not, we are going to assume the data is normal. So the sample mean will become approximately normal if the sample size is 30 or more. So sometimes I may not tell you that the data is normal, but I may say I have 100 people. So 100 is bigger than 30, so we are just going to assume it's normal and we'll keep doing the same thing we have been doing. Okay. I know I don't have a ton of time. Do you guys care if I go ahead and do these last 2 examples? Because you know we're going to have this packet for a while. This is the long section. Tomorrow's section is way shorter. But. All right, so suppose that the mean time for an oil change at a 10-minute oil change joint is 11.4 minutes. Standard deviation is 3.2. So that is for my original population. In a random sample of 35 oil changes, describe the sampling distribution of the sample mean. So sample mean, I'm talking about X bar. I did not tell you anywhere that this was normal, but N is bigger than 35. So I can assume it is approximately normal because my N is bigger than 30. Okay, so as long as N is bigger than 30, we're just going to assume it's normal and keep going with it. So now we do it the same as the others. When I ask you to describe the sampling distribution, some of your homework will ask for that. I'm wanting you to tell me that it's normal, find the mean, and the standard deviation. Those are the three components I want. So the mean for my sampling distribution is the same as the original, 11.4. Standard deviation is the original divided by the square root of N, which is 35. And we get 0.5409 if I round. So part B, I want the probability that the mean, so that mean is X bar, is less than 11. So change it to a Z. So 11 minus my mean divided by my standard deviation. So I want the probability Z is less than negative 0.74. Less than is what the table gives me. So we just have to read it. And so it is 0.2296. So are they really a 10-minute oil change place? No, they're saying they'll get done in 10 minutes. There's only a 23% chance it'll be less than 11 minutes. So definitely not likely. All right, one more. Last one. So the mean weight gain during pregnancy is 30 pounds, standard deviation of 12.9. An obstetrician obtains a random sample of 35 low-income patients and determines the mean weight gain was 36.2. Does this result suggest anything unusual? So, did I tell you it's normal? No, but N is 35, that's bigger than 30, so we can say it's normal. Okay, I'm talking about the mean, so that's X bar, so I need my mean and standard deviation for X bar. So what's my mean? 30. Standard deviation was 12.9 divided by the square root of N. So we get 2.1805. Okay, I'm trying to decide if it's unusual that they gained 36.2. Did they gain more or less than we would expect? More. Okay, so you have to think about how we want to find this. So their weight gain is up here. If I find the probability that you're less than that, is that really going to tell me anything? No, because I expect you to gain less than that. So if I want to figure out if this is unusual, let's find the probability that you gain more than the 36.2. So we've got to get our Z. We only need 2 decimal places for Z's, 2.84. So I want the probability Z is bigger than 2.84. So for greater than, what do we do? 1 minus. Look up 2.84 on the table. Okay. So is my result unusual? Yes, it's less than 5%, so this is definitely unusual. Some possible explanations. This could mean either we have a poor sample, so for some reason we just picked a sample that was very different than the original population, or it may indicate the actual mean is different for this group. You know, our data is flawed in some way. We got a very unusual result. So either the problem is our sample, or the problem is this sample really